There is a story we tell ourselves, and it is one of the most seductive, most cinematically beautiful, and most physically dangerous stories our civilization has ever embraced. It goes something like this. Out there, just beyond the orbit of our one fragile world, sits a second canvas, a rust-colored sphere waiting patiently in the dark like a lighthouse at the edge of an ocean we have not yet learned to cross. We look at its photographs and see something that feels almost familiar, almost home. We see valleys and mountains, and the long, cold whisper of ancient riverbeds carved into the skin of another world. And in that almost familiar geometry, we find comfort. We find escape. We find the beginning of what feels like an answer to the oldest and most urgent question our species carries in its chest, which is, what do we do when this world is no longer enough? I want to gently, but with full physical precision, dismantle that story for you tonight. Not because wonder is wrong, not because ambition is foolish, but because the universe has spent 13.8 billion years writing its laws in the cold, indifferent language of mathematics, and those laws do not negotiate with our comfort. They do not soften their edges for our poetry. And when we arrive at Mars, not in our imaginations, but in our bodies, those laws will be waiting for us with an efficiency so complete, so instantaneous, so geometrically final, that we will not even have the luxury of a dramatic death. We will simply cease in the span of a breath, because the physics of that world were never arranged to tolerate us. Imagine for a moment something impossibly delicate. Take a single snowflake, one of those microscopic crystalline architectures that requires a perfect, narrow band of temperature, humidity, and pressure to even exist for a matter of seconds in the open air. Now take that snowflake and drop it into the churning white-hot core of an industrial blast furnace, one of those titanic chambers where steel itself loses its molecular coherence and flows like water. Do not just imagine the snowflake melting. Understand what is actually happening at the level of physics. The furnace is not hostile to the snowflake in the way a predator is hostile to prey. It is not pursuing it. It is not even aware of it. The environment simply operates according to its own thermodynamic rules, rules that are utterly and completely incompatible with the structural conditions that allow the snowflake to exist. The moment the snowflake enters that space, the surrounding physics erase it. Not gradually, not with warning, instantaneously, because the furnace was never built around the snowflake's needs, and the snowflake has no leverage against the temperatures that govern that chamber. That is the relationship between a living human body and the surface of Mars. Precisely, perfectly, and without a single metaphorical concession, that is what the physics describe. Let us begin with the atmosphere, because the atmosphere is where the arithmetic of death begins most immediately. The Martian atmosphere is not thin in the way we might describe mountain air as thin. It is not a lesser version of what we know. It is, by the functional standards of human physiology, the nearest thing to nothing that still qualifies as something. The surface pressure on Mars hovers around 6 to 8 millibars. Earth maintains an average surface pressure of approximately 1,013 millibars. That means the Martian air pushing against your skin at any given moment is less than 1% of what your biology was constructed to survive. This brings us to what physicists call the Armstrong limit, named after American physician Harry George Armstrong, who identified in the mid-20th century a precise thermodynamic threshold that no unprotected human body can cross and survive. That limit sits at approximately 19 kilometers of altitude above the Earth's surface, where atmospheric pressure drops to 63 millibars. At that pressure, the boiling point of water descends to 37 degrees Celsius, which is, not incidentally, the standard operating temperature of the human body. This is not a coincidence of poetry. This is the mathematics of phase transition colliding with the mathematics of biology, and the result is catastrophic. Below the Armstrong limit, the liquids in your body do not merely feel uncomfortable, they boil. The moisture on the surface of your eyes and lungs begins to vaporize. The water in your cellular tissue undergoes rapid phase transition from liquid to gas. Your blood, that warm, pressurized, beautifully engineered river running through your veins, begins to foam. The medical term for what follows is ebulism, and it is the physiological equivalent of your entire biological plumbing system attempting to expand beyond the structural capacity of the vessels containing it. Your tissues swell. Your circulatory architecture fails. The elegant hydraulic precision of your vascular system collapses in seconds, not from violence applied from outside, but from the simple, cold fact that the thermodynamic conditions necessary to keep that liquid no longer exist. Mars does not sit near the Armstrong limit. Mars sits catastrophically far below it. The surface of Mars, in terms of its atmospheric pressure, is functionally equivalent to standing at roughly 35 kilometers above the Earth's surface, deep in a zone where no exposed human biology has ever functioned or ever will. And this is only the beginning. The second physical reality waiting for us on Mars is the thermodynamic arithmetic of its temperature, and this arithmetic is not merely uncomfortable. It is a machine designed by pure physics to strip thermal energy from any warm object with an efficiency that borders on mechanical cruelty. The average surface temperature of Mars sits around negative 60 degrees Celsius, though it swings with brutal range from approximately negative 125 degrees at the poles in winter to a deceptive high of around 20 degrees near the equator at midday. That upper range sounds almost survivable until you understand what the thin air actually does to heat transfer. On Earth, our dense, layered atmosphere acts as a thermal buffer. It holds heat, it distributes it. It creates the conditions under which insulation can function, because insulation works by trapping air, and trapped air retains thermal energy with reasonable efficiency when the surrounding medium is dense enough to slow the transfer. On Mars, that medium barely exists. The thin, sparse atmosphere cannot hold heat. It cannot distribute it. And this means that any warm body, any object maintaining a temperature above its environment through internal processes, is exposed to an almost direct thermodynamic sink of enormous depth and zero thermal memory. The cold on Mars does not creep. It does not settle in gradually the way a winter evening might descend. It attacks at the molecular level through the simple, relentless mechanism of kinetic energy transfer. Every molecule in a warm material is vibrating at a rate that corresponds to its temperature. When that material is exposed to a colder environment, the kinetic energy bleeds outward until equilibrium is achieved. On Mars, the equilibrium point is far below anything compatible with mechanical function or biological survival. Seals fail, lubricants solidify, polymers become brittle, electronic junctions crack. And the organic membranes of living cells, those beautifully engineered lipid bilayers that maintain the chemical separation between life and non-life, stiffen and rupture. Your suit, no matter how engineered, is a thermal object operating inside a planetary-scale heat sink. The margins of error between functional insulation and catastrophic thermal loss are narrower than anything we have tested at the scale of sustained human habitation. And this is before the third physical reality even enters the calculation. The ground itself is trying to kill you, not metaphorically, not as poetic framing. At the level of chemistry and electrostatics, the Martian regolith is one of the most aggressively hostile material surfaces ever characterized in the history of planetary science. The soil of Mars, that fine rust-colored powder that photographs so beautifully in orbital images, is heavily saturated with perchlorate compounds. Perchlorates are oxidizing salts, and at the concentrations found in Martian soil, they are acutely toxic to human biology. They interfere with thyroid function. They disrupt iodine uptake at the cellular level. They damage the endocrine architecture that regulates nearly every hormonal process in the human body. Concentrations measured on Mars by instruments like the Phoenix lander and the Curiosity rover reach levels hundreds of times above what would constitute a serious public health threshold on Earth. But the chemistry is not even the most immediate problem. The electrostatics are. The Martian surface is continuously bombarded by solar ultraviolet radiation and by charged particles from the solar wind. Radiation that on Earth is absorbed and deflected by our magnetic field and our thick atmosphere. Mars has neither of these shields in any meaningful sense. The result is that the fine perchlorate dust on the surface becomes electrostatically charged, acquiring a surface charge that causes it to cling to everything it contacts with an adhesive, efficiency that mechanical filtration systems have enormous difficulty defeating. This dust is not passive. It does not simply sit on the ground waiting to be avoided. It is lofted into the thin Martian air by wind, by rover wheels, by the footfalls of any hypothetical surface walker, and it drifts invisibly through the atmosphere in concentrations that seep through filtration matrices, corrode sensor arrays, degrade optical surfaces, and infiltrate the mechanical seals that stand between a human being and the near vacuum outside. Every Mars mission we have conducted with robotic instruments has confirmed that dust management is one of the most persistent, most technically challenging, and most stubbornly unresolved engineering problems in Martian surface operations. And robotic instruments do not need to breathe. They do not have mucous membranes. They do not have alveoli. They do not have cellular tissue that will respond to perchlorate infiltration with the systematic biochemical dismantling of their hormonal and respiratory function. You do. And the dust does not know that. It does not care. It simply obeys the electrostatic forces that the physics of that irradiated, unshielded surface have imposed upon it, and those forces will deliver its chemical payload to your biology with the same indifferent precision that the cold delivers its thermal stripping and the vacuum delivers its phase transitions. Here is what I find profound about all of this, and I mean that without any softening of the physics. The terrifying completeness of Mars as an environment hostile to life is not a tragedy, it is data. Extraordinarily beautiful, precisely arranged, mathematically awe-inspiring data about the conditions under which life can exist. Every physical law that makes Mars lethal is, when read in reverse, a portrait of what Earth has done right. The atmospheric pressure that would boil your blood on Mars tells you precisely how extraordinary it is that Earth maintains a surface pressure calibrated to keep liquid water liquid inside biological systems. The thermodynamic sink of the Martian cold tells you precisely how remarkable it is that Earth's dense, energetic atmosphere acts as a planetary thermal buffer that sustains the narrow temperature band in which chemistry can organize itself into self-replicating structures. The perchlorate-charged regolith tells you precisely how astonishing it is that Earth's magnetic field and ozone layer intercept the solar radiation that would otherwise charge and poison the ground beneath every footstep you have ever taken. We did not earn these conditions. We did not engineer them. We arrived inside them, and they built us, and we are so deeply embedded inside their mathematical precision that we cannot feel them any more than a fish can feel the water. But Mars offers us something the fish will never have. It offers us the contrast, the view from outside the conditions that allow us to exist, a view so unambiguous, so physically total in its hostility, that it strips away every comfortable illusion we carry about the ease of life and forces us to see with full intellectual clarity how narrow and how extraordinary the physics of our home truly are. The cosmos is not our enemy. It is simply not arranged around our survival, and that distinction, held clearly and without flinching, is not a reason for despair. It is an invitation to a more honest, more rigorous, and more genuinely awe-filled relationship with the universe we actually inhabit, a universe where the mathematical conditions that allow a single cell to maintain its chemical